Haoyu did his master in biomedical engineering at Shanghai Jiao Tong University. Currently, he's working on AI compilers and agentic systems at Intel. One of his earliest work is 3D foundation model, which is SAM-Med3D. In addition, I still remember that in addition to the nice code base, they also created a large-scale 3D dataset and make it publicly available, which is great contribution to the community. So, uh, okay, yeah, without further ado, how it's yours?
Thanks to the introduction from Professor Ma, and I will introduce the baseline of SAM-Med3D for our challenge.
Sorry for
Uh,
interruption. Could you please switch your slide to
oh,
the
okay,
content
okay.
mode?
Wait a minute. Okay. I think it's no need to introduce myself. I'm Wang Haoyu from Intel and Shanghai Jiao Tong University. Here's the table of contents for my slides. I will first introduce SAM-Med3D and show some implementation details of our baseline and give my suggestions for our further improvement. First is about this. What is SAM-Med3D? SAM-Med3D is a general-purpose interactive segmentation model designed for 3D medical images. It is pre-trained on a large-scale dataset, and our motivation is to build an efficient and accurate segmentation model. Our key features can be summarized into three parts. First, we use a very large dataset to train our model. This large dataset focuses on two modalities, CT and MRI. The second point is that we use very diverse targets in our dataset. Our dataset contains over 200 categories, and specifically, there are over 200 organs and more than 20 lesions. The third part is our model supports very simple interactive method to help you very easily to use it. We only support the click-based prompt. Here's all the stuff for which contribute to our works. Very thanks to them. The first introduction is about our model architecture. SAM-Med3D is a very early stage work for adapt SAM into the 3D biomedical image. So we use a very straightforward solution to adapt SAM direct to 3D. We just change the corresponding 2D parts into their 3D version. The detailed the details of the layers is the positional embedding, convolution layers, and the normalization blocks. For the other blocks, we just keep them unchanged. Details can be found in our code. As for the details of pre-training of SAM-Med3D, we have published our training dataset. We named it SAM-Med3D, and the dataset contains 22,000 3D images, over 100,000 3D masks from more than 70 public datasets, and 8,000 private data collected by us. Our dataset includes two modalities. They are CT and MRI, and covering over 6 anatomic structures. The details is listed in the figure here. They are about some organs and lesions in the chest, in the abdominal areas, and some bone architecture. As for the details of the training process of SAM-Med3D, different from many previous work that adapt them to 3D biomedical images, they train based on the pre-trained weight from SAM. We directly train from scratch on our large-scale dataset. The data usage details can be seen in the slides. We use a two-stage pre-training process. The stage 1, we train the model for 800 epochs on the full training set. It's about 131,000 masks. After this stage, we train our model for 200 epochs with a filtered training set. It's about half the full training set. As can be seen in the experimental result, the two-stage training can effectively improve our performance on almost all anatomically structures. And the next part is about the implementation details of SAM-Med3D baseline for our challenge. To align the data format and normalization into our SAM-Med3D code base, we need to resample all NPZ data into the target spacing we pre-trained our model. It's 1.5 millimeter. And to further clean the data, we remove the hard-to-see targets based on the physical size. All targets in our training set will be larger than the threshold. Even if the original threshold of the challenge is 100 volts, we propose a more strict threshold to further clean the data. Another point is that the original SAM-Med3D model doesn't support the bounding box promote to guide the model to select the target. So we use a workaround for B-box. We use the center point of a 3D bounding box as the first positive point prompt to guide the model. For the training process of SAM-Med3D, we do a simple training process. We just fine-tune the full parameter of SAM-Med3D from the checkpoint SAM-Med3D Turbo. It's the published version of our SAM-Med3D model with the previous mentioned two-stage pre-training. And we just fine-tune the model on the 10% data version of this challenge for 200 epochs. After the training of our model on the provided data, the inference process can be summarized into into 4 steps. First, we resample the test data into the target spacing we pre-train our model. Then we crop the image into the set sliding window size based on the first prompt. No matter it's a point prompt or a bounding box, we just crop the window from the center. Then we just predict the segment from the on the cropped window. Then we resample the prediction back into the original space and attach the data, the prediction into the original position and get the final prediction. Okay, I think the process is quite simple, so we get to the suggestion for further improvement. Here's my 3 suggestions to further improve the SAM-Med3D baseline. We think the first suggestion is about the prompt encoding. Since I mentioned before, SAM-Med3D doesn't natively support bounding box prompt, even if not evaluated in this challenge. I think it may be help to add a native support for bounding boxing during your training. And I will further introduce how we can add the bounding box support. The second suggestion is about training methods. As I mentioned before, the training process of SAM-Med3D is just full parameter fine-tuning. So you may try some dedicated fine-tuning methods like LoRa, or you can froze the encoder or anyway. Another tip is that you may use a well-trained unit or other unit structure to better encode the image. The second suggestion is that for the inference method, we think you can use a larger window size to improve the reception field of the model. The original window size of SAM-Med3D is 128 and is quite small for some large targets, although it's resampled. So maybe use some sliding window structure or just use zoom out structure like Yuxin shared in his SigWall. This may be okay to better handle large targets. But I think you need to consider the trade-off between the speed and accuracy because doing zoom out or sliding window will significantly increase the inference cost. That's all the information for the baseline of SAM-Med3D, and here's some useful links. I will show you some detail about the code. For this challenge, we provide a detailed tutorial to help you develop from SAM-Med3D. It is a branch of the official repo of SAM-Med3D. Just follow the tutorial. You can quickly info and modify the code. As for infer and evaluation, I think is no need to introduce because you just need to run the Docker or just okay, you need to run the Docker. From the source code, you need to set up the environment, and the setup steps are listed here. And one point I want to mention that is the fine-tune checkpoint is being uploaded to Hugging Face. You may fine-tune from the SAM-Med original checkpoint, and you can also fine-tune your model just from our newly published checkpoint here. And for the training requirements, we measured the data here. You just need a GPU with more than 16 gigabyte RAM to run the training process. And if you have more GPUs or with larger DRAM, you can first set bigger batch size and next improve the window size I mentioned. I think that's all I want to share. Maybe we can get into the Q&A.
Yeah, thank you, Haoyu, so much. Any questions from the audience? I have a minor point here for the, could you please return back to GitHub page?
Sorry, I didn't hear you.
Could you please return back to the GitHub page?
Oh, okay. Here.
Yeah, scroll up more to, yeah, so for the Docker command, I want to clarify that the memory is 32 gigabyte instead of 8 gigabyte. Sorry for the 8 gigabyte setting was for last year's laptop segmentation setting. Now this year we extended it to 32. I apologize. This was my mistake. I didn't change it in the website before.
Okay. It is changing now.